Good morning, everyone. This is Mrs. Hanin Khair from Al Shumukh International School. I'll be explaining the second topic of Term 2 curriculum, Quantitative Kinetics. We will start by recalling the factors that affect the rate. So, as you already know from grade 11, there are 5 factors that affect the rate of a reaction. Concentration. As the concentration increases, the rate of the reaction increases because the frequency of the collisions between the particles increases. The second factor is the pressure. As the pressure increases, the volume decreases. This brings the particles into closer proximity, increasing the frequency of collisions and therefore the frequency of successful collision. The third factor is temperature. As you know, increasing the temperature allows the particles to gain kinetic energy, therefore they will collide more and with a higher energy. So therefore we will have a bigger fraction that are colliding with the minimum sufficient energy. The fourth factor is the catalyst. Using a catalyst provides an alternative pathway with a lower activation energy. Therefore we have more proportion or a higher proportion of particles that are colliding with the minimum activation energy. Finally, the last factor is the surface area. The surface area, as the surface area increases, the size of the reacting particles decreases. So therefore the rate of the reaction increases because basically that's for solid particles. So the reaction is occurring at the surface of the particle. Increasing the surface area increases the frequency of collisions. The rate of the reaction now. What's the meaning of the rate of the reaction? The rate of the reaction is, before we used to say that it's how fast a reaction is taking place. Now we need to define it in another way. The rate of the reaction is measured in terms of how quickly a reactant is used up or a product is formed in a unit of time. So if you want to express it ratio-wise, you can see that the rate is the change in the concentration over the change in the time. Now, as you can see, the units of the rate is expressed in mole per decimeter cube per second if you are measuring the time in seconds. If you are measuring the time in minutes, it's gonna be mole per decimeter cube per minute minus 1. Right? So, in general, for any reaction, AA plus BB plus CC plus DD, where A capital, B capital, C capital, and D capital are the reactants and the products, and the small letters are the stoichiometric coefficients, that is the balancing. So the rate of the reaction is equal to the rate of consumption of A over A, which is the stoichiometric coefficient of A, which is equal in turn to the rate of consumption or disappearance of B over the coefficient B, equals to the rate of formation of C over the coefficient of C, equals to the rate of formation of D over the coefficient D. So, square brackets represent the concentration in mole per decimeter cube, delta represents the change, and T represents the time. So instead of saying rate of disappearance of A, we're gonna use this formula to say that change in the concentration, which is delta A over delta T, minus 1 over A means it's over the stoichiometric coefficient A. Now, why we are using minus? Reactants decreases with time. The amounts of reactants decrease with time. So therefore, the variation will be negative. let's say you're starting with 1 mole of A. After a certain time, let's say 5 minutes, you're gonna have 0.8 moles of A. So therefore, if you do the variation, the change, it's gonna be negative. And it's impossible to have a negative value for the rate, because rate is basically the speed, and speed can never have a negative value. The lowest possible value for the rate is 0. Once you know the rate of disappearance or formation of any of the reactants and the products respectively, you can find out the rate of the reaction just by dividing by the coefficient itself. We will see examples later on. Now, the rate equation. What's the meaning of the rate equation? The rate equation is a mathematical equation that relates the concentrations of the reactants to the rate of the reaction. Let's say we have any reaction, A plus B, giving products. Now basically you don't care about the products because products do not affect the rate of the reaction. The only thing that affects the rate are the reactants, the concentration of the reactants. So the rate equation of the above reaction is given by, this is the rate, equals to K is a rate constant. You don't have to worry about K, it's a constant that doesn't change even when changing A and B, the concentrations. The only factor K depends on is temperature. And you don't have to worry about it, it will be either given or you can find it simply by simple mathematical calculations. Now A is the concentration of reactant A, and A small is the order of the reaction with respect to A. That has nothing to do with the stoichiometric coefficient of A. That has nothing to do with the balancing. Please make sure, do not confuse between balancing and order of a reaction with respect to a reactant. In a while, in coming pages, we will learn how to find out the order of a reaction for a certain reactant. So once again, the rate, alright? So we have the rate of a reaction is equal to K, the constant, multiplied, there's no plus here, so it's a multiplication, multiplied by the concentration of the first reactant raised to the rate order of this reactant, multiplied again by the concentration of the other reactant raised to the order of the reaction with respect to this reactant as well. Now, how many orders do we have? For your case, guys, the orders are, or you are most likely to meet orders 0, 1, or 2. That's very easy. If the rate order is 0, anything raised to the power Z of 0 is 1. So basically, when any reactant, when the order of a reaction with respect to any reactant is 0, this reactant is not affecting the rate of the reaction. So let's say A power 0. This means that changing A would not affect the rate because A power 0 is 1 regardless what is the concentration that you are using. So if the order of a reaction with respect to a reactant is 0, this means that the concentration of that reactant does not affect the rate of the reaction. So if the order of the reaction is 1, this means whatever you do to A applies to the rate. If you double A, the rate will double. If you double A, the rate will double. If you triple A, the rate will triple, and so on. And finally, if the order with respect to the reactant is 2, this means that if you double that concentration, the rate would quadruple, would go 4 times up, which is 2 power 2. If you triple A, then the rate would increase by a factor of 9, 3 power 2. So whatever you apply to A, it's going to be raised to the power of 2 if the rate order is second order with respect to that reactant. So the rate constant, as we already said, is a constant. It's the constant of proportionality in a rate equation. It's unaffected by changes in concentration. It changes when changing temperature of the reaction, adding the catalyst, or changing the catalyst. As the temperature increases, that's very important information, the value of the rate constant increases. It increases exponentially, and it will be explained later on. Alright, so basically, so far, you just need to know the definition of the rate in terms of changing the concentration per unit time, how the rates are related according to stoichiometric coefficients. Once you know the rate of disappearance of any reactant or the rate of formation of any product, it's gonna be equal according to stoichiometric coefficients. And the rate equation, just you need to know what are the meanings of A small, B small, and K. Now, questions. The rate equation for a reaction between P and Q is this: rate equal Kp squared Q. How will the rate changes if the concentration of P is doubled? Now, what's the rate order of P? As you can see, P is power 2. So therefore, the reaction is second order with respect to P. So when you double P, this is going to be multiplied by, the rate is going to be multiplied by 2 power 2. So the rate is going to be multiplied by 4. So the rate is going to quadruple. Alright? Because 2 power 2 is 4. Now the concentration of Q is tripled. As you can see, Q is power of 1. So therefore, whatever applies to Q applies to the rate. If the concentration of Q is tripled, then the rate is going to be multiplied by 3, or it's gonna increase by a factor of 3. Now, what if the concentration of both P and Q are tripled? What's gonna happen? So the rate is going to be multiplied by 3 power 2, and then it's gonna be multiplied by 3 power 1. So what's gonna happen is the rate, so the rate is gonna be multiplied by a factor of 3 power 3. So the rate times 27. So the rate will increase by a factor of 27. Right. Now, another question. In a reaction between R and S and T, when R is doubled, the rate is unchanged. So even if you're changing R, the rate is not changing. This means what? This means that R is not affecting the rate. So therefore, the order of R is going to be 0, because doubling R is not changing the rate. When S is quadrupled, the rate is increasing by 16. So if S is multiplied by 4, the rate is multiplied by 16, which is basically 4 power 2. So therefore, the rate order of the reaction with respect to S is second order. For T, when T is halved, the rate is halved. So whatever applies to the reactant applies to the rate. So therefore, T is first order, or the rate of the reaction with respect to T is first order. So therefore, we can say now that the order. The orders are for S, it's second. For R, it's first. It's 0. And for T, it's first. So the rate equation now is equal R equals K, the rate constant, S power 2, and then T, and that's it. We don't include R because R is not affecting the rate. Alright, S power 2 because the rate order of the reaction for S or with respect to S is second order. And T power 1 because whatever applies to T is applied to the rate. When T is halved, the rate is halved. Same thing. Alright. So that's basically the information. You just need to know how to relate the effect of doubling the concentration or changing the concentration on the rate, whether it's 0, 2, 1. That's it. Now, how to work out the order of the reaction from experimental data. To work out the rate equation, series of experiments are conducted where the initial concentrations of reactants are changed one at a time. You can't know the factor of a certain or the effect of a certain concentration if you change two concentrations at the same time. You have to change one reactant at a time. So in questions, this data is normally presented in a table. To calculate the order for a particular reactant, two experiments are chosen. You choose the experiment, basically you change such that one reactant is changing at one time. If the concentration is doubled and the rate stays the same, then the order is 0. If the concentration is doubled and the rate doubles, then the order is 1. And if the concentration is doubled and the rate quadruples, then the order is second order with respect to that reactant. So let's consider this example. Basically this should be here, this arrow. I'll just show it quickly. So A plus B plus 2C, it's forming D plus 2E. Alright. We conducted 4 experiments. Each time we were changing 1 or 2 reactants and we were measuring the rate. Now, how to measure the rate? It's something you don't have to worry about right now. We'll study it later on. You are just presented, you will just have this data and you need to analyze this data. So we need to find out the order of the reaction with respect to A. So if you are finding out A, you have to fix B and C. You have to choose experiments such that only A is changing. And then study the effect of changing A on the rate. So let's check the experiments. Where do you have experiments where B and C are constant? As you can see, if you consider 1 and 2, here A is basically doubling. Alright, so this one is times 2. This is constant, this is constant. What's happening to the rate? As you can see, the rate is also multiplied by 2. Now if you're not good in math and you can't figure out very quickly, just divide the big value by the small value on the calculator, you'll get the value. 0.2 over 0.1, you'll get 2. So when A is doubled, the rate is doubled. Therefore, what's the rate order with respect to A? It's first order. Yes, that's right. Now, we need to choose another 2 experiments where B is changing and A and C are fixed. Let's have a look. Let's consider reaction 1 and reaction 3. Sorry, experiment 1 and experiment 3. Now A, as you can see, A is not changing 0.1 to 0.1. B is changing. So what's happening to B? As you can see, it's going from 0.5 to 1. So it's basically doubled. C is not changing as well. So if the rate is going to change, that's only because of B. What's happening to the rate in this case? It's multiplied by 4. So basically when the A when B is doubled, the rate is quadrupled, right? This is not a minus here. Okay, great. So when B is doubled, the rate quadruples. So therefore, the rate order of the reaction with respect to B is second order. So now I have first order with respect to A, second order with respect to B. I still have one reactant left, which is C. I need to choose two experiments where A and B are not changing and only C is changing. Considering 1 and 4, A is not changing, 0.1 and 0.1. Considering B, between experiments 1 and 4, as you can see as well, it's going from 0.5 to 0.5, so it's not changing. The only concentration that is changing is that of C. It's going from 0.25 to 0.5, so it's multiplied by 2. What's happening to the rate? 0.1 to 0.1. So even if C is changing, B and A are not changing, the rate is not changing. So therefore, the rate order with respect to C is 0 order. So whatever I said is written here if you want to read it again. So the overall rate order is, if we write here next to C, 0. So as you can see, it's gonna be K A B square. We don't include C because it's not it's not affecting the rate. All right. So it's 0. It looks like 6. I'm gonna write it again. Oh, okay. Never mind. Fine. Now what's the meaning of the overall order? The overall order is found out by adding the individual orders. So 1 plus 2, it's equal to 3. 1 plus 2 is equal to 3. So the overall order is computed by adding the individual rate orders. Alright. Sometimes it gets more trickier. However, we will do one more example on the easy one and then we'll go back to the trickier example. So let's have a look on this one. I'll just zoom it a little bit. Fine. Great. So we have two reactants, X and Y. And we are changing the concentration of each one in several experiments. And we have to study or to find out the rate equation. So we have to find out the rate order of the reaction with respect to X. So I have to choose two experiments where Y is not changing. Very simply, it's 1 and 2. So I'm gonna see here, you're going from 0.1 to 0.2. So it's multiplied by 2. What's happening to the rate? It's going from 0.002 to 0.008. So it's multiplied by 4. What's the relation between 2 and 4? As you can see, the rate order of the reaction with respect to X is second order. Now I need to fix X and check the effect of changing Y, if there is any. So I'll consider the experiments 1 and 4. between 1 and 4, x is not changing. However, y is changing from 0.1 to 0.2. What's happening? It's multiplied by 2. What's happening to the rate? Nothing. So therefore, the rate order with respect to y is 0. So the rate equation, I'm gonna write it here. Okay, scroll down a little bit. So now I have r equals to k x squared. So x is the only reactant that is affecting the rate. Y is not affecting the rate. Even if you change y, nothing is gonna happen. You can choose 1 and 5 as well. If you choose 1 and 5, look at this. X is not changing, the rate is not changing, because y has nothing to do with the rate. Only if you change x, the rate is going to change. Alright. I think that makes sense now. One more example before we do the hard one. Alright. Again, I have two reactants, A and B, and I need to find out the rate equation for this reaction. So choosing 1 and 2, B is not changing. As you can see, A is multiplied by 3, so A is tripled. What's happening here? If you go from 5 to 45, it's multiplied by 9. So when A is tripled, the rate is multiplied by 9, which is 3 power 2. So therefore, the rate order with respect to A is second order. Now I have to fix A and change B. You can use either 1 and 3 or 2 and 4. Any is applicable. So if choosing 1 and 3, what's happening to the B? It's doubling. So the rate of the concentration of B is doubling, and when concentration of B is doubling, the rate is doubling. You're going from 5 to 10. So therefore, whatever is applying to B applies to the rate. When B doubles, the rate is double. So it's first order. So therefore, what's the rate equation? R equals to K A squared B. Alright. You can choose also going from 3 to 4. As you can see, it's tripling. This one is multiplied by 9 as well. So therefore, the reaction or the rate order of the reaction with respect to A is second order, with respect to B is first order, and that's the rate equation. Now we'll go back to this one. Here in this reaction, as you can see, X is never constant. So it's a little bit more difficult. Alright, so how to figure this out? We'll find out X first because Y is fixed, it's constant between 1 and 2. So what's happening to X in the first and the second experiment? Going from 5 to 10, so it's doubling. Here, going from 15 to 30, as you can see as well, it's doubling. So the rate order with respect to X is first order. It's first order with respect to X because when X doubles, the concentration of X doubles, the rate doubles. Now how to find out the effect of Y? We will choose experiments 1 and 3. What's happening here? You're going from 0.05 to 0.2, so it's times 4. What's happening here? It's going from 0.1 to 0.2, so it's 2. Now if you divide 2.4 times, if you divide 2.4 over 15, you will see it's computing it very quickly. 2.4 over 15, 2.4 over 15, it's 16. Okay, never mind. Let's use other experiments. Let's use 2 and 3. It's quite easier. So I'll just erase these. Alright. Fine. So if you're choosing 2 and 3, alright. As you can see, from 2 to 3, x is doubling. So here, going from this one to this one, it's doubling. And this one is doubling as well. What's happening to the rate? 2.4 over 0.3, it's multiplied by 8. So you already know that the rate order with respect to x is first order. So when x is doubling, the rate supposedly should double. However, the rate is multiplied by 8. So where are the other 4 coming from? They are coming from y, the effect of y. So if I'm gonna write it here, 8 is equal to 2 times 4. So therefore, this is the effect of y. Alright, so when y was doubling, the rate was quadrupling. So therefore, the order of y is second order. So therefore, x is 1 and y is 2. So the rate equation is k x y squared. Of course, I don't forget to write r. So again, for this part, 2, you were doubling x, going from 0.1 to 0.2. The rate was multiplying by 8. The effect of x is 2 power 1 because x is first order. Alright? So therefore, instead of having 0.6 as a value, we're having 2.4. So where are the other part coming from? It's 2 times 4, right? 8 is 2 times 4 because you know already 2 is there. So the other thing, it's 4. So when you doubled y, the factor that affected the rate, or the rate increased by a factor of 4, which is 2 power 2. So therefore y is power 2. This is called the combined effect. Sometimes you might have this, but it's not quite common. That's basically the rate equation and how you find it graphically. Okay?